welcome back. In this video, we are going to look at some of the application that is related to the open loop. We all know what is a open loop system where it doesn't have a feedback. So in this example, we are going to look at controlling the speed of the servo motor. So as you can see, we have a diagram which represent how a servo motor operates. And we want to derive a transfer function, and from this transfer function we are going to see what is really happening with the input and the output of the system. So this physical system can be represented using a block diagram. And we all know in the block diagram we should have the input, and the input must be connected to a controller. And in this diagram we can see that the controller is nothing but the potentiometer. So a potentiometer is nothing but a variable resistor, and it is now connected to the power amplifier. We can have the power amplifier, and finally it is connected to the servo motor, and we should have the output. Since this is the open loop, there are no feedback in this system. So when we look at the input that is our desired angle that we need to turn the knob. When you look at a potentiometer, we have a potentiometer and it has a variable point in which when we increase the potentiometer to one side, it will increase the resistance, we can say towards this side. And if we turn the knob towards this side, we should decrease the resistance. So that is how a potentiometer is made, and the symbol can be seen like this. So from this block diagram we can also see that the output is the speed of the servo motor, and we can apply the system parameters such as the gain of the system and the signal. So the input of the system can be the angle, and we can say theta I is the angle, and into the potentiometer, and from the potentiometer we can have a voltage as an output. And when the voltage is passed through a power amplifier, we can have a signal output we can label as P, such as the power to the servo motor. And the output of the servo motor we can represent using the variable N. So theta I, V, P, and N, they represent the parameters we can call as a signal. So we have theta I is the signal input, V is the output voltage of the potentiometer, P may represent the power to the servo motor, and N represent a signal that is measured, that is the speed. And also we have the potentiometer, we can say beta 1, beta 2, and beta 3. Those represent the gain of the system. So a potentiometer can be regarded as one system, and the power amplifier can be regarded as one system, and the servo motor can be one system. Why do I say it is a system? Because if we describe a potentiometer, we can say if we apply an angle to the knob of this potentiometer, we should have a voltage output, and we give the gain beta I, which represent the gain or the transfer function of a potentiometer. And remember, when we talk about the gain, that means we analyze the signal in the time domain. And when we say transfer function, that means we analyze the system in the frequency domain. So we can see that the transfer function of the system or the gain can be calculated such as beta I is equals to V on theta I. This can represent the gain of the system. And if we say beta I is equals to V of S over theta I of S, now this is in the transfer function format. So if we want to find the relationship between the angle theta of the potentiometer and the voltage output, so when we measure, we can say initially this is 1, 2, 3, and 4. So this one is theta is equals to 0. We should have 90 degree, 180 degree, and 270 degree. So with the relationship between the resistance and the voltage output, so if we have, let's say, 1000 ohm potentiometer, so if we divide by 4, it is corresponding to 90 degree, which can be equals to 250 ohms, and 180 we can say 500 ohms, and 270 we can say 750 ohms, and towards this side we should have 1000 ohms when we full rotate the knob. Imagine that this system is connected to 5-volt supply and to the ground. So this is the point of our connection. So we can determine the relationship such that the connection is the output, and we label as V. And now we can find the relationship between the angle of the potentiometer, which will now corresponding to the voltage output of the potentiometer. So what we are interested in is to find the gain, which is the beta I of this potentiometer, and how can it relate to the angle of the knob. When we find beta, we can now actually find the voltage output, which will be equals to beta I times the angle theta. Now this will be our system equation for the potentiometer. For the theta, when it is related to the voltage, we normally use the circuit which is called the voltage divider. And this voltage divider is responsible for varying the voltage output of the potentiometer. And the circuit diagram can be shown as follows. So we have the positive 5 volts as the input, and then we have the V, which is the output of the system. And we can have the variable resistor, so we have R1 and R2. So the equation for the voltage output of the voltage divider, which is equals to, let's say, V out, which will be equals to R2 over R1 plus R2 multiplied by the voltage input. So you can see from this equation that this portion now represent the beta I, which represent the gain of the system in time domain. So the V out is proportional to the V in, such that when we decrease beta, that means the V out will be equals to the V in. So mostly in such circuit, when we are trying to remove the proportional sign, we normally add a constant. and this constant is called the beta I, and it can be derived from the second parameters such as the resistor. And we all know that the resistor R2 has a value between 0 ohms to 1000 ohms. So what will be the value of R1? So as a designer, you will now find what is R1, which will now corresponding to the voltage output, which will fed into the power amplifier. However, practically the definition for the voltage divider is such that the Vout must be equals to the fraction of Vin. So having that in mind, if we now are to find R1 such that the output, if it is a fraction of the input, and we can say that it is a fraction of the input towards 5 volts. If we have during the computation, we said R1 is now equals to 333.3 ohms. And we all know for a 5 volts input, we should have 3.75 volts at the output when the resistance of R2 is 1000. And we can substitute the Vout, which is now equals to 1000 ohms over 333.3 plus 1000 ohms times 5 volts. The Vout now should be equals to or equivalent to 3.75 volts. So that can be a fractional output when we have R1 is equals to 333.3 ohms. So this will be the maximum output, and when we vary the resistor from 1000 towards 0 ohms, we should have a decrease in this value. So we can now plot the relationship between the theta and the voltage output and the resistance as follows. We have the theta I, and we can have the voltage out and the resistance. So for 0 degree, 90 degree, 180 degree, 270 degree, and so from this data, when it is 360, we say 1000 ohm, where the Vout is 3.75 volts. And for a 270 degree, we should have 750 ohms, 500 ohms, 250 ohms, and let's say equivalent to. Now when we turn the knob to 270 degree, what will be the voltage output? It will be equivalent to 3.46 volts, and 500 ohms, we should get 3 volts. For 250, we can have 2.14 volts. And now for the resistance, which is 0 ohms, actually there is no 0 ohms resistance. However, you will have small resistance. And let's say if we say 0.1 ohms, we should have around 0 volts at the output. So this gives us a relationship between theta I and the Vout. So with this data, we can now be sure that when we turn the knob from 0 to 360, that means we are increasing the voltage output. That means increasing the resistance R2, we normally increase the voltage output. And this voltage output is now fed to the power amplifier. So we can say this is our potential meter data, and it is derived from this equation. So this will be our actual circuit for designing the potentiometer. Now let us look at the power amplifier. So now we can see that the power amplifier, we now have the V out, which is the data from the potentiometer into the power amplifier. And this power amplifier has the ability to control the servo motor. When we look at the servo motor, we can also see that the requirement for the servo motor, we can have the voltage is proportional to the speed. And now the voltage will be the data, which is the P variable, and the speed is represented using the N. So in order to obtain this P, this will be the output of the power amplifier. So example, we have the servo motor, which have the max speed of 2000 revolution per minute. And to achieve this max speed, we should have the max voltage. Suppose that we need 9 volts to achieve 2000 revolution per minute. So that means the maximum voltage of the servo motor will be 9 volts. So we have to have the maximum voltage output, which is 9 volts from the power amplifier, in order for the servo motor to run at the maximum speed. So we have this data, we can now correspond with the input voltage to the power amplifier. So from there we can calculate the beta 2 gain of the amplifier. So how can we design this? We know that the maximum input to the power amplifier will now be 3.75 volts. So when we have input 3.75 volts, we know that the output should be 9 volts. So with this relationship where we have P must be equals to beta 2 dot V. So we have data such that P and beta. So to find beta 2, we simply say P over V, where P can be 9 volts divided by the V, which is 3.75 volts. So from there we can calculate the gain of the power amplifier. So the gain must be 2.4. So that means this power amplifier is made up of an electric circuit. And this electric circuit should be designed such a way that the gain must be 2.4. Or a power amplifier can also be an electrical circuit such as a potentiometer or the operational amplifier, in which it has the capability to amplify the voltage parameter of a signal. So we can also draw the relationship in a table, since this power amplifier is designed to have a gain of 2.4. Theta I, the V, the P, and the N, we can now discuss using this table. So we have the system parameters that can be plotted, and we want the system to operate by following this data in the table as we discussed. So 0, 90 degree, 180 degree, 270 degree, and 360 degree. And we have 0 volts, 2.14 volts, 3 volts, 3.46 volts, and 3.75 volts. So the P, we previously discussed that we should have 9 volts here, which now correspond to 2000 revolution per minute. So if we want to calculate with respect to our beta, which is 2.4, we should now complete the table. We have 8.3 volts, 7.2 volts, 5.13, and 0 volts. So in that case, we can see the speed can be 0. And remember the relationship between the input to the servo motor and the speed, we should be able to determine beta from these two values. So we can have now the servo motor and beta 3, which we have 2000 revolution per minute, and the input should be 9 volts. What will be the beta 3? Will be equals to 222.2. This will now be the gain of the servo motor. So by using this data, we can have 1139.9 revolution per minute and 1599.8 revolution per minute, and we can have 1844.3 revolution per minute. So this entire system will now operate based on this data. So our servo motor system, we can have the servo motor system will operate based on the output speed and the input, which is the angle theta. So we can say when we have 0 degree, the output speed will be 0 revolution per minute. So when we turn the knob to 90 degree, the output speed will be 1139.9 revolution per minute. So when we turn the knob to, for example, 270 degree, that means the revolution will be 1844.3 revolution per minute. And when we fully turn the knob to 360, now we are at the maximum speed, which is 2000 revolution per minute. So from our entire discussion, you can be able to see how the angle theta will affect the speed of the servo motor. And in this case, this is the open loop system where we don't care about the stability of the system. Even though we have some disturbance, this type of disturbance, such as heat in the system or any voltage uncertainty that is happening in the servo motor, those parameters will affect the output speed. For example, if heat is generated in the system, this heat can represent the loss of energy, and the loss of energy in the system can decrease the performance of the output. But in this video, I want to show you that you can be able to represent a system mathematically by considering the parameter and the signal gain in and out of the system to produce the corresponding speed. So this is nothing but the response of our system, and this is our desired input. So the input and the output, they have a relationship such as the angle and the speed. So I believe with this video, at least you can be able to appreciate why we need mathematical model to represent the performance of a system. Because later on, when we look at a system in a closed loop, where by then we are now focused on the stability of a system, that means any disturbance that is happening to the circuit will affect the output. However, we have the feedback, which can help us to control the servo motor to maintain the speed such that when we have a specific angle, the speed must always be correspond to this particular angle of the input, such that if we have disturbance and this one is 1800 revolution per minute, this is due to the disturbance. So we have a feedback that will measure, and there will be a error because our target is to have 2000 revolution per minute. However, the actual output is 1000 revolution per minute. So there must be some error correction in the circuit. That's why we need a closed loop system. This is a simple explanation in the time domain where we use actual values to represent. In our later video, we will look at how we can represent the system in terms of the use of the transfer function.